Hello, 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 everyone, and welcome to the Ben's Chem Videos Sunday night live stream. That's right, I have moved my live stream from Friday to Sunday for reasons that I explained in an announcement that I uploaded a couple of days ago. I think this would be a pretty good move overall, and I certainly appreciate you guys being flexible and joining me on a new night of the week. So we're doing this on Sunday nights now. So we're going to talk about chemical equilibrium. I'm very excited to kick things off. Last live stream series was all about chemical kinetics, and I think it's very fitting that we continue with chemical equilibrium. Just a couple of things to get out of the way real quick. One is that I came very, very close to canceling this live stream. That's right, my very first Sunday night live stream almost didn't happen. Why? Because, well, I have a daughter who is 6 months old, and she just got her booster shots for, the 6 months booster shots, or it's kind of a routine thing for babies, and she has been very, very upset all weekend long. Imagine a screaming, crying baby in your ear all day, every day for 2 days straight. That has been a reality for my wife and I. But anyway, enough about my personal sob stories. Let's get back to the chemistry. The other thing is I wanted to give a special shout out to a one Jacob Halber. This one is for you, sir.
So Jacob had the idea that I should bring back my sulfur hexafluoride tank and have it make an appearance in my live stream, and so here you go, Jacob. Doesn't necessarily have any particular relevance to chemical equilibrium, but nevertheless it is very fun to use, and my tank is running fairly low, so I want to get as much good times out of it as I can. So thank you very much for the suggestion, Jacob, and look at me, I'm a man of my word, listening to the people. All right, so with that out of the way, let us jump right into chemical equilibrium. Here we go. So this is Chemical Equilibrium, Volume 1. By the way, if anybody wants to chime in, please feel free to drop a message in the chat, or better yet, you can call into the show via Discord. If you don't have Discord, it's very, very easy to download to your phone or to your computer, whatever you happen to be watching this on. And if you like, you can call into the show. I would love the opportunity to talk to you one-on-one. All right, so without further ado, here we go. It's Chemical Equilibrium, Volume 1. So imagine a game of paintball, right? Imagine a paintball game. I don't know if you ever played paintball before. I have a couple of times, and it is exhilarating. If you've never played paintball, I would highly recommend it. I actually got invited by my coworkers recently. We went out, we played paintball, we had a great time. They invited me again another time, and then I wasn't able to go because I was still recovering from my surgery, so I was kind of bummed out about that. But if you imagine a paintball game, right, you got this blue team over here, you got this red team over here, and they're shooting paintballs at each other. Blue team is shooting paintballs at the red team is shooting paintballs at the blue team, and imagine that these two teams are shooting paintballs at one another at the exact same rate, right? So imagine that the amount of paintballs from blue to red in a given period of time are the exact same as the amount of paintballs shot from red to blue in a given period of time. The rates of those paintball firings are equal. So the analogy here is that this is a lot like chemical equilibrium. So chemical equilibrium is concerned with reactions that are reversible. They can go one way from reactants to products, and they can also go the other way from products to reactants. The reactants can react together to form products, but the products can also react together to form reactants. Now, not all chemical reactions are irreversible. Like, let's say if you have two liquids reacting together to form a gas, and then the gas in an open container, and then the gas floats away. Well, there's no way that gas is going to float back down and react to form the liquids again. So some reactions are irreversible. Other reactions, like the one we're looking at right now, where we have hydrogen and oxygen reacting to form water, are reversible. So the hydrogen and the oxygen react to form water, but then the water molecules can also react with each other to form the hydrogen and oxygen. Now, the term dynamic equilibrium, chemical equilibrium, dynamic equilibrium, they're kind of like synonyms, right? I like the term dynamic because it implies that
the reaction is never just sitting still. The reaction is occurring, both reactions, the forward reaction where the reactants become products and the reverse reaction where the products become reactants, those are occurring at the exact same time. They never stop. Now the term equilibrium is the condition in which the rate of the forward reaction is equal to the rate of the reverse reaction. So I like talking about equilibrium right after kinetics because there's a little bit of understanding of kinetics that helps to understand equilibrium, because kinetics is all about reaction rates, and so equilibrium is defined as the condition at which the rate of the forward is equal to the rate of the reverse reaction. So that's what this double arrow means. That's what this double arrow denotes. This double arrow means that the hydrogen and the oxygen are reacting to form water at the exact same speed, the same rate, as the water is reacting to form hydrogen and oxygen. So we can look at this graphically, and I'm going to put myself right in the middle here. There I am, right in the middle, so I'm not in the way. Okay, see, I'm slowly getting the hang of this. So we can look at this graphically. So imagine that we start out just with hydrogen and oxygen. We don't have any water yet, and then we allow them to react. Well, what's going to happen? Well, the hydrogen and the oxygen are going to react. Their concentrations are going to decrease. Now, back when we looked at chemical kinetics, we understood that in general, the concentration of a reactant depends upon the rate, or in other words, the rate of a chemical reaction depends upon the concentration, i.e., as the reactants react and become less concentrated, the rate of that reaction slows down, right? And so you can see here that the slopes of these curves, this is concentration versus time, the slopes of these curves for the reactants hydrogen and oxygen are decreasing as the reactants become consumed, and then you can see the water is being formed over here. But notice that at a certain point, the curves flatten out and the rates essentially become zero. They're constant, right? And so that's what we call dynamic equilibrium. It's the point at which the rates of the forward and reverse reactions are equivalent. Notice that the concentrations at equilibrium are not equivalent. The concentration of water at equilibrium is much, much higher than the concentration of hydrogen and the concentration of oxygen, right? So for a reaction to be at equilibrium, that says nothing about the relative concentrations of the reactants and products, only that the rates of the forward and reverse reactions are the same. So it's very, very important that we keep that in mind going forward. As I said before, if anybody has any questions or any comments or any concerns, please feel free to drop a message in the chat, or better yet, call into the show via Discord. There is a link right down there in the description. All right, so let's keep going. So here we go. I'm going to move myself back here. Now, one way that we can quantify the relationships between the concentrations of the reactants and products at equilibrium, at the condition in which the forward and reverse reactions are the same, is by using something called the equilibrium constant, which we call capital K. So you might be thinking, well, K, doesn't that stand for the rate constant when we were looking at kinetics? Well, that was a lowercase k. The equilibrium constant is a capital K. So if you're one of those people who likes to write in all caps all the time, you might not want to do that when it comes to chemistry, because you might mean to say one thing and then end up saying something completely different because you chose to do to write a capital letter instead of a lowercase letter. So anyway, so the equilibrium constant K, what is it all about? So the equilibrium constant K, if you have a general reaction at equilibrium where we have A moles of A reacting with B moles of B to produce C moles of C and D moles of D, where the lowercase letters are the stoichiometric coefficients and the uppercase letters are the reactants and products themselves, the equilibrium constant, K, is equivalent to this expression here, where we have the concentration of the product C raised to the power of the coefficient, lowercase c, times the concentration of the product D raised to the coefficient of lowercase d, the coefficient. That expression, that whole product, divided by the product of... Now, it's kind of unfortunate that the term product refers to the result of a multiplication problem, because I'm talking about product multiplication, but then I'm also talking about product like products of a chemical reaction. So it's a little bit confusing. So I'll try to be as clear about that as I can. So again, we have C raised to the C power times D raised to the D power divided by the product of the multiplication of the reactant A raised to its stoichiometric coefficient, lowercase a, times
the reactant B raised to its stoichiometric coefficient B. So that is the equilibrium constant, right? So if we wanted to look at a problem like this, so we were just looking at this reaction here, this equilibrium reaction where we have hydrogen and oxygen reacting together to form water at equilibrium. If we wanted to write an expression for the equilibrium constant associated with this reaction, how would we do it? Well, I think this is a good opportunity to go to the whiteboard. So give me a second here. I will copy this stuff and we'll cruise on down to the whiteboard and bang out this problem. So here we go. It's been a little while since I've done this. All right, gonna resize it. There we go. Okay, so we are asked to express the equilibrium constant for this reaction. Well, remember, the equilibrium constant is simply the concentrations of the products raised to their stoichiometric coefficients divided by the concentrations of the reactants raised to their stoichiometric coefficients. So in this case, K is going to be equal to the concentration of water, H2O, raised to its stoichiometric coefficient, which in this case is an understood 1, so concentration of water to the first power, or just simply the concentration of water, divided by the same thing for the reactants, right? So we're going to have concentration of H2, and we're going to square that because the coefficient in front of the hydrogen is 2, concentration of H2 squared, times the concentration of O2 to the first power, or just simply the concentration of O2. So this here would be the expression for the equilibrium constant for this reaction. So this is pretty straightforward. Again, if you have any questions, feel free to chime in. Otherwise, we're going to continue to move on. So I think we all have an understanding of how to express equilibrium constants given the balanced chemical equation. Oh, and there's one more thing that I wanted to point out about this relationship between the balanced chemical equation of a reaction and the expression for the equilibrium constant. This relationship has a name, and it's called the law of mass action. Let me write that down. Law of mass action. Sounds like some suspenseful movie or something, like coming this summer, Law of Mass Action, starring Keanu Reeves. I don't know. Something like that. That's what it reminds me of. But anyway, we're going to move on. My jokes are terrible. That's why we're moving on. Okay, so if we go back to the PowerPoint, let's see. All right. So, okay, that's great. We know how to express the equilibrium constant for a chemical reaction given its balanced chemical equation. Well, so what? What does the value of K mean? What is the significance of the equilibrium constant? Well, you can probably figure this out just by sort of thinking about the formula for K. Notice that the K is a ratio. It's a ratio of concentrations of products to concentration of reactants. And so if K is, let's say K is much, much larger than 1. K is a very, very large number. Well, what does that imply? Well, since this is a fraction, this is a ratio, right? K being much, much larger than 1 implies that the numerator, the products, is much, much larger than the denominator, in which case the concentrations of the products are much, much higher than the concentrations of reactants. And so in this case, the forward reaction is favored, and this reaction proceeds nearly to completion. Almost all of the reactants react together to form products at equilibrium. Now, if K is much, much less than 1, then it's kind of like the opposite, right? Then in that case, the reverse reaction is favored, and there's not many of the reactants that react together to form products at all. That represents a scenario in which the denominator is much larger than the numerator of this fraction. And so we have a very, very small value of the rate constant. So this would be a reactant-favored equilibrium. The reverse reaction is favored. And as you have probably already guessed, if K is close to 1, if it's almost equal to 1, then neither the forward nor the reverse direction are favored, and the reaction proceeds about halfway to completion at equilibrium. And again, equilibrium, that just means that the rate of the forward reaction is equal to the rate of the reverse reaction. Equilibrium does not say anything. I repeat, does not say anything
about how fast the reaction occurs. That was chemical kinetics. Kinetics is associated with how fast the reaction occurs, right? Equilibrium constant, all that tells us is how far the reaction has proceeded, right? How far the reaction has proceeded once the rate of the forward and reverse reactions are the same. Really, really want to make that very, very clear. All right, so moving on. So there are some situations where you might be asked to manipulate a chemical equation and manipulate the equilibrium constant for the equation accordingly. So there are really three possible manipulations of a chemical equation that you can perform, and you would have to carry that over through with the equilibrium constant. One of them is reversing an equation, so the products become reactants, the reactants become products. One of them is multiplying the equation by a factor, so you would multiply all the coefficients in the balanced chemical equation by a factor. What does that do to the equilibrium constant? And then finally, another scenario, another manipulation of a chemical equation that you might have to perform would be adding more than one equation, two or more equations together to form an overall equation, an overall reaction. So how would we arrive at a rate constant for that overall reaction, knowing the rate constants for all those reactions that we added together? So we're going to go through each one of these scenarios, and I'm going to sort of explain how the mathematics works along the way. By the way, if anybody has any questions or anything at all to say, please feel free to drop it in the chat. And by the way, also, if you find value in this live stream, I would certainly appreciate you slapping a like on this. It goes a long way to help discoverability. And if you're feeling super generous, you can consider sending a super chat, or even better, supporting the stream through Streamlabs. There's a link in the description. Streamlabs donations, they take a much lesser cut than YouTube super chats, but I am happy with whatever I can get. All right, so moving on. We're talking about manipulating chemical equations. So one manipulation, the first one that we looked at in that little bulleted list, was if you reverse a chemical equation. So if you reverse a chemical equation, what does that do to the equilibrium constant? Well, it inverts it, right? If you reverse the chemical equation, you invert the equilibrium constant, right? So to demonstrate this, I'm going to go to the whiteboard. And so let's say we have, right? Let's say we have a chemical equation that looks like this, where we have A plus 2B reacting at equilibrium to form 3C, right? So this is just a general equation, right? Now, we know from the law of mass action that this reaction, or that the equilibrium constant associated with this reaction is going to be the concentration of C to the third power cubed times the concentration of A, divided by the concentration of A times the concentration of B squared. So we know that this is the expression for the equilibrium constant for a reaction that looks like this, right? Now, if we had the reverse reaction, so I'll do that in blue. So let's say we have the reverse reaction, products become reactants, reactants become products. We would have 3C reacting to form A plus 2B, right? And so this reaction, I'll call it K minus 1, the reverse rate constant, or not rate constant. See, here, I just got it mixed up too. The reverse equilibrium constant would be concentration of A times concentration of B squared divided by the concentration of C cubed, right? And so we can see here that the expressions for the equilibrium constant between the forward reaction and the reverse reaction are flipped. All we've done is we've just taken the reciprocal, the inversion of one equilibrium constant to arrive at the other. And so we have this relationship here where the K minus 1 is simply equal to 1 over K, right? So if you have an equilibrium constant and you want to know the equilibrium constant for the reverse reaction, all you got to do is take 1 and divide it by that original equilibrium constant, and voila, there you are. There's the equilibrium constant for the reverse reaction. So I hope everybody's following, because we are going to move on with the second scenario. If I just go back to the PowerPoint real quick. Okay. So the second scenario is that if you multiply an equation by a factor, so in other words, if I take all the coefficients of a balanced chemical equation at equilibrium and I multiply that by some factor, what you're going to do is you're going to raise the equilibrium constant to the power of that same factor. So just like in the previous example, I'm going to show you again how the mathematics works behind this. So if we go back to that same scenario, I wish I didn't erase it a moment ago because I'm using it again. So if we go back to that same scenario, right, where we have, let's see, A plus 2B reacting to form C, right? And of course, the equilibrium constant for this is K is equal to concentration of, wait, I said 3C. That's what it should be. 3C, right? Concentration of C cubed divided by concentration of A times concentration of B squared, right? So that's the equilibrium constant for the original reaction, right? Now, imagine that I multiply this equation by some factor which we will call n, right? So the resulting equation would be n times A plus 2n times B reacts to form 3n times C. So again, if you multiply an equation by a factor, you're multiplying all of the coefficients in that equation by the same factor, right? So how does that affect the equilibrium constant? Well, again, if we apply the law of mass action once again, we get that K, I'll just call it K prime. K prime is equal to concentration of C to the 3n, right, raised to its coefficient, divided by the concentration of A to the n times the concentration of B to the 2n, right? So that's what this would be. So just got a message in the chat that says, can your next series live stream be related to light reactions and that stuff? I mean, light equations? Yeah, send me an email. Send me an email, and I'm not sure what exactly you're talking about. I'm not sure if you're talking about like photochemistry. I'd be happy to talk about that stuff, but yeah, just let me know in an email what exactly you're talking about, and I would love to oblige, just like I did with that sulfur hexafluoride tank. Okay, so getting back to this problem here. So all we've done so far is we've expressed the reaction, the balanced chemical equation, as if it's multiplied by a factor, and then we just use the law of mass action to express the equilibrium constant associated with that reaction after having been multiplied by a factor, right? So this expression here simplifies down, just because of the properties of exponents, to the concentration of C cubed divided by concentration of A times concentration of B squared, this whole thing to the power of n, right? And so we arrive at the relationship that we talked about before, where we have K prime is equal to the original equilibrium constant K to the power of n. Whichever factor it was that you multiplied by the original equation, you take the equilibrium constant, you raise it to that factor, and that gives you the equilibrium constant associated with your new equation. All right, so I hope that was simple enough, because we are going to move along, move along. All right, go back to the PowerPoint. Okay, so the third possibility, the third type of manipulation that you might be asked to perform on a chemical equation and understand what to do with its equilibrium constant has to do with adding equations together. So if you add equations together to obtain an overall balanced chemical equation, what do? Well, you're going to multiply the equilibrium constants for those individual summed reactions to arrive at the equilibrium constant for your summation, for your overall reaction. And so I can once again go to the whiteboard and explain how this works from a mathematical point of view. So let's say that you have two reactions that you're adding together. The first reaction, let's say that it is A reacting to form 2B, and then let's say that you have 2B reacting to form 3C, right? So those are your two equations that you add together, and then your 2B's would cancel once you add those together, and the overall equation that you would get would be A is reacting to form 3C, right? So what would the equilibrium constants look like for these reactions? Well, this one, I'll call it K1, is equal to, what is it going to be? What do you think it's going to be? It's going to be concentration of B squared over concentration of A. And then this one down here, K2, I'll call it K2. Not to be confused with something that you should never ingest. The second equilibrium constant is going to be concentration of C cubed divided by concentration of B squared, right? And this one down here, which I'll call KO, just for overall, is going to be concentration of C cubed divided by concentration of A, right? So notice that if we take K1 and multiply it by K2, and I'm going to try to do this little fancy lasso thing here. I'm going to lasso this K2 expression right here, and I'm going to bring it over there. So imagine I'm multiplying these together, right? Then you see my concentration of B squared terms are going to cancel, and I'll be left with concentration of C cubed over concentration of A. So it makes sense, right? There's a reason why multiplying the equilibrium constants for the individual reactions arrives at the equilibrium constant for the overall. So I could have just told you guys that that's how it works, right? I could have just told you the rules, but I always like to make sure I'm explaining things and make sure people kind of get an understanding mathematically of how this works. I don't like to just spoon feed you a formula and expect you to follow it. I really, really want you to understand the mathematics behind it. So I really hope you have you've appreciated that and you've found value in it. All right, so we're going to move right on and continue. By the way, thank you everybody who's in here. Thank you very much for being in here and contributing to the chat. By the way, if you do call in via Discord, I don't always check. I don't always check to see who's in the call-in show waiting room. So if you are in the call-in show waiting room and you're like waiting for me to take your call, just type a message in the chat. Let me know that you're in there and I can take your call. I would love to hear from you. So, all right. So we're going to continue. Here we go. Okay, so we've talked at length about how to carry over the equilibrium constants when you manipulate chemical equations in 3 different ways. So let's do a problem where we put that knowledge to work. So it says to consider the following reaction where we have 2COF2 reacting to form CO2 and CF4, and that has an equilibrium constant of 2.2 times 10 to the 6th at 25 degrees Celsius. Now, the at 25 degrees Celsius part might seem insignificant, but it's not. Equilibrium constants do depend on temperature, and we will certainly talk about that in a later live stream, but just understand for now that equilibrium constants do change with temperature. So the problem asks us to calculate the equilibrium constant for this reaction below at the same temperature, where we have 2CO2 plus 2CF4 reacting to form 4COF2. So the main idea here is that this equation for which we're trying to find the equilibrium constant is the result of one or more manipulations to this equation up here in which the equilibrium constant is already given. Got a message from Varun. It says, "Hi, sir." Hello, very happy to have you here. Just banging out some equilibrium problems. Thanks for joining us. So, all right, so here's what we're going to do. We're going to, whoops, I'm getting ahead of myself a little bit here. Okay. So I'm going to take this and I'm going to move it over to the whiteboard and just need to resize it. And there we go. Okay, so we need to come up with a plan for how we're going to manipulate this equation to get from the reaction that we started with to the reaction that we end up with. And we need to make sure that we understand those relationships involving the equilibrium constant along the way. I don't know about you, but this kind of reminds me of like those delta H Hess's law problems where you manipulate delta H based on manipulating chemical equations. That's the impression that I got when I first started studying this. Type a message in the chat if you feel the same way, or not, whatever you want. All right, so we can clearly see, right, that we're going to have to reverse this chemical equation, right? Because in the example that we're given, we have COF2 on the left, and in the example, in the target equation, I'll just call this the target equation from here on out, we have the COF2 on the right. So we definitely have to reverse this equation. That's not all that we have to do, but that's at least one thing that we have to do. So why don't we start with that, right? So if we take this equation up here, right, and we reverse it, well, what are we going to end up with? Well, that equation is going to be CO2 plus CF4 yields 2COF2. Now, for brevity, I'm choosing to leave out the states of matter. They're all gases. If you're doing this on a test or something, depending on how nitpicky your professor is, I would definitely recommend including the states of matter, but it doesn't really make much of a difference in the context of this particular problem. So to speed things up, I'm going to choose not to include those little G's in parentheses at the end of every chemical formula, right? So again, if we take this equation up here and we reverse it, we get this equation down here that I've just written in blue. Now, if we recall from those rules that we discussed earlier, when we reverse a chemical equation, we invert the equilibrium constant. We take 1 over the equilibrium constant, right? And so for this reaction, K is going to be 1 over this original equilibrium constant, 2.2 times 10 to the 6th, right? 1 over 2.2 times 10 to the 6th. So we're going to put that in a calculator. Now, it's important that whatever calculator you're using, that you are familiar with how to apply scientific notation in that calculator. You do not want test day to be the first time that you use this calculator. You want to be very familiar with it because not all calculators are created equal. Lucky for me, I did my homework and I prepared I prepared for this ahead of time, so I've already done this. And the number that I ended up with for this new equilibrium constant is, what did I get? I got 4.5. By the way, if I'm incorrect, it's entirely possible that I'm incorrect, people. If I'm incorrect, please let me know. 4.5 times 10 to the minus 7, right? So this is our equilibrium constant upon reversing the equation that we started with. Now, we still have to do more work, right? Because this equation is not identical to the target equation. To get our target equation, we have to multiply this equation by a factor. We have to multiply this by a factor of, looks like it's going to be 2, right? So we need to take this equation and we need to multiply that by a factor of 2, right? And so in doing that, what we're going to end up with is an equation that looks like this. It's going to be our target equation, right? 2 CO2 plus, 2 CO2 plus 2 CF4 yields 4 COF2. So that's our target equation. That's what we want. And remember from the rules that we talked about earlier, when we multiply an equation by a factor, we're going to raise the equilibrium constant to the power of that factor. So this equilibrium constant that we just calculated here, what we're going to do is we're going to take that and we're going to square it. We're going to raise that to the second power. And the number that you end up with, and again, I would highly encourage anybody who has a calculator who might be watching to perform this calculation for yourself just to make sure that I haven't done it incorrectly myself. The number that I ended up with is 2.0 times 10 to the minus 13. So that is what I ended up with, 2.0 times 10 to the minus 13. So that is kind of a typical problem that you might encounter involving manipulating chemical equations and manipulating the equilibrium constants accordingly. All right, so I hope that's been helpful. Let me know either way. If it's been helpful, let me know. If it hasn't been helpful, let me know. Any kind of feedback is good. Any kind of feedback is important. It is absolutely necessary that I understand where we're all at and what I'm doing well and what I'm doing poorly. All right, so we're going to move on and go back to the PowerPoint. We got a couple more things before we wrap up for the night, and then we can kind of open it up for just a casual discussion if you guys are interested. So here we go. All right, so we've banged out that problem. Now, okay, so here's where it gets a little interesting. So far, we've talked about how to express the equilibrium constant in terms of concentration. However, it turns out that you can also express the equilibrium concentration, or the equilibrium constant in terms of pressure. So if we return back to the example that we started with in the very, very beginning, where we have hydrogen and oxygen reacting together to form water, the equilibrium constant for that one was concentration of water divided by concentration of hydrogen squared times the concentration of oxygen. We can be more specific and we can call that K sub C, in other words, the equilibrium constant with respect to concentration. But we can also express the equilibrium concentration in terms of pressure using something called partial pressures. So at this point, we're kind of digging back to our understanding of gases. So remember, the partial pressure is like the individual component, the individual contribution that each component within a mixture of gases contributes to the total pressure. And there's this thing called Dalton's law of partial pressures, which says that the total gas pressure is equal to the sum of the partial pressures of the individual components that make up the mixture. And so this P sub H2O, P sub O2, P sub H2, P sub whatever just means the partial pressure of. And so if we wanted the equilibrium constant with respect to pressure, that would be the partial pressure of water. In this case, it would be the partial pressure of water divided by the partial pressure of hydrogen squared times the partial pressure of oxygen. So it's basically the same thing as the equilibrium constant with respect to concentration, the same relationship, the law of mass action, products raised to their coefficients divided by reactants raised to their coefficients, only instead of using concentrations, we're using partial pressures, right? Now, it turns out that you can actually derive a relationship between the concentration, or excuse me, the equilibrium constant with respect to concentration and the equilibrium constant with respect to pressure, right? And so that's what we're going to do right about now. So I hope this is going to be a pretty lengthy derivation. I hope I don't lose anybody. And by lose anybody, I mean I hope nobody tunes out, and I also hope nobody clicks away. But I understand that with lengthy derivations, both of them are possible. So again, what we're trying to do here is we're trying to derive a relationship between the equilibrium constant for concentration and the equilibrium constant for pressure, right? So in order to do that, there's a couple of relationships that we're going to have to understand. We're going to have to go back into the gas laws and this and that. So if we think about an individual component, right? If we think about an individual component, an individual gas, I'll call it A. The concentration of that gas is going to be equal to the amount of that gas in moles, which I'll call N sub A, divided by the volume of the container in which that gas exists, right? Concentration is equal to moles per liter. The moles of that gas over the volume, right? Now, if you recall, there's this thing called the ideal gas law. If you've gotten this far in your chemistry education where you're talking about equilibrium, you probably know the ideal gas law equation by heart. Can anybody in the chat say it for me? I don't know. I don't know how long I should wait because I know there's kind of a delay between when I say something and when you hear it. So I don't want to stall or get boring or anything. But I'll just go ahead and say it. The ideal gas law equation is PV equals nRT, right? The product of the pressure and the volume is equal to the amount of the gas in moles, which we call N, times the gas constant R, which is 0.08206 liters times atmospheres over moles times kelvins, multiplied by the temperature in kelvins, right? So that's PV equals nRT. So understanding the ideal gas law equation and understanding that the concentration of a gas is equal to the amount of that gas in moles divided by volume, we can arrive at this equation down here where we have the partial pressure of that gas, which we'll call P sub A, times the volume is equal to the amount of that gas in moles, N sub A, times RT. So again, all this equation is doing is just kind of connecting these two equations together. Kanan Crystal says, I did not remember that sign. Oh, that's that's okay. It's okay. No worries. Nothing to be ashamed of at all. So, okay, so partial pressure of gas A times volume equals the amount of that gas in moles times the product of the gas constant and the temperature, right? And so if we rearrange this equation, right, then we get the partial pressure of that gas A. So all we're doing in this case is we're just dividing both sides of this by the V, by the volume. Partial pressure of that gas A is equal to the amount of that gas in moles over volume times RT. Now, if you look up here, we see that the concentration of that gas, of the gas A, is equal to that N sub A over V. And look, we have that N sub A over V right here. And so what I can do is I can take this little term right here, and I can substitute the concentration of A for that. So we arrive at this equation here where we have partial pressure of gas A equals concentration of A times RT. Everybody still following me? Cerelia B says same here. Oh, well, like I said, nothing to be ashamed of. By the way, thank you guys for being here. Cerelia, I do not recognize you, so if you're new, welcome. But if you're returning, then welcome back. I really appreciate you being here. And that goes for everybody. Thank you so much for joining me. I truly appreciate it. Appreciate your participation and your feedback. Okay, so if we arrange this equation and we isolate this concentration term, right, we get that the concentration of A is equal to the partial pressure of A over RT, right? So this is where the derivation starts to get very, very lengthy. Christian Barrios is in the chat, says, hello, Ben. Hello, Christian. Very good to see you. Welcome. Thanks for being here. Appreciate it. So, all right, so now we have an expression for the concentration of an individual component, an individual reactant or product in the gas phase in terms of the partial pressure of that gas divided by RT, right? So remember that if we have this general reaction, right, where we have A moles of A reacting with B moles of, whoops, got ahead of myself there, B moles of B at equilibrium to produce C moles of C plus D moles of D, right? The law of mass action tells us that the equilibrium constant for this is concentration of the products C and D raised to their coefficients little c and little d divided by the concentration of the reactants A and B raised to their coefficients little a and little b, right? And so, like I said, this is where it starts to get really lengthy. I think my wrist is going to fall off when I write this. So, and by the way, this is Kc, right? The equilibrium constant in terms of concentration. Again, this is all stuff that we saw before at close to the beginning of the presentation, right?
So now what we're going to do is we're going to take this expression over here, this partial pressure expression, concentration in terms of partial pressure, and we're going to substitute it into this law of mass action equation. And so what we end up with, or not end up with, but the next step that we get is that the concentration, or excuse me, the equilibrium constant with respect to concentration is equal to, and this is going to be a very big expression. So I'm going to try to set this up. There's a lot of parentheses and fraction bars in this expression here. So in this case, it's going to be the partial pressures of the products, C and D, partial pressure of C, partial pressure of D. Each of these is going to be divided by RT, and these are going to be raised to the coefficients little c and little d. And it's going to be the same thing for the reactants, partial pressure of A, partial pressure of B, divided by RT, divided by RT, raised to the little a and little b. And again, all that we've done here, is we've substituted this expression for concentration, which includes the partial pressure of the individual gas, and we have taken that and just inserted it everywhere where there's a concentration term in brackets here. We've inserted this term right here, this fraction, right? So I hope everybody is still with me. So we can clean this up a little bit. Just by factoring out some terms, right? And we can factor out the 1 over RT term. And so what we end up with is partial pressure of C, the product, raised to the power of little c, times partial pressure of D, raised to the power of little d, divided by partial pressure of reactant A raised to the little a, times partial pressure of B raised to the little b. And each of these, I'm kind of running out of room here, but hopefully I don't, is 1 over RT. Whoops. Each of these is multiplied by 1 over RT. And up here, we have C plus D. And down here, we have A plus B. Because if you're multiplying terms with exponents together, you multiply the individual terms and you add the exponents together. So again, I hope this isn't too confusing. A lot of rearranging and algebra and stuff like that. But again, if anybody has any feedback to give, now and anytime is the time. All right. So we can clean this up even further. And again, I got to make sure I don't run out of room here. And I might actually be able to do this in a more efficient way. Instead of writing everything out, I might be able to just lasso in what I need here. Let's see if I can do that. All right, I'll just write everything out. This isn't working like I thought. Canon Crystal says, I did not like trying to answer those. We did a shortcut, if I remember. Yeah, listen, hey, if shortcuts work well for you, I'm not hating on it. But me personally, I like to intimately, thoroughly understand the reasons why the shortcuts work. Like, I use shortcuts myself when I was studying chemistry. There's no shame in it. But the important thing is, like, if you forget the shortcut, can you derive your way out of it? If you can, then you're in good shape. If you can't, well, your grade might suffer as a result of that, right? So again, all we're doing here is just cleaning up this equation further. And if you'll just bear with me for a second, this expression, this Kc, is going to be equal to partial pressure of C raised to the little c times partial pressure of D raised to the little d divided by partial pressure of A raised to the little a times partial pressure of B raised to the little b. This whole thing times 1 over RT raised to the power of C plus D minus the sum of A and B, the coefficients. So if you can see here, what I've done here is, you know how like when I said earlier, if you multiply terms together, you add the exponents. If you divide terms, then you subtract the exponents, right? So that's where this C plus D minus the sum of A and B comes from right here. So again, I haven't really done anything other than just kind of arrange this equation to clean it up a little bit. Now, this term right here, and I'll circle it in green, I guess. This term right here, where you have the partial pressures of the products raised to their coefficients divided by the partial pressures of the reactants raised to their coefficients, that is K sub P. That's the equilibrium constant with respect to pressure, right? And so if we take this equation and rearrange it, so if I, yeah, I guess I could just erase that, right? I can just erase that and just put the Kp in it, right? So if I erase all of this, that whole thing, right? That whole thing is equivalent to K sub P, right? So Kc is equal to K sub P times 1 over RT raised to the power of the sum of the coefficients for the products minus the sum of the coefficients for the reactants, right? So if we rearrange this equation one final time, we will get the relationship that we're looking for, which is that the K sub P, whoops, I'm kind of running into myself there a little bit. K sub P is equal to K sub C times the product of the gas constant and temperature, RT, raised to the power of what we call delta N. Delta N is just a very shorthand way of, I'll just write it in down here. So delta N simply means the sum of the coefficients of the products C and D minus the sum of the coefficients of the reactants A and B. Okay, so that's our relationship between the equilibrium constant in terms of pressure and the equilibrium constant in terms of concentration. Now, notice that if there are just as many moles of gas on the product side as there are on the reactant side, then delta N becomes 0. And this term, this RT to the delta N becomes 1 because anything raised to the 0 power is 1, and then Kp becomes equal to Kc. So again, if the moles of gas on the product side and the reactant side are equal, then the Kp is equal to Kc. The equilibrium constant in terms of pressure is the same as the equilibrium constant in terms of temperature. So that's kind of an interesting fun fact, right? So we have one more thing that we're going to do. We're just going to apply this formula. We're going to apply this relationship between equilibrium constant with pressure and equilibrium constant with concentration. And we're going to do that in a problem. And then that'll be it for tonight. And then we'll come back next week and continue. So if I grab my mouse here, I'm going to go back to the PowerPoint. Okay. All right. So once again, we're going back to the original equilibrium reaction that we started with, hydrogen reacting with oxygen to form water. And it says that the equilibrium constant with respect to concentration is 1.25 times 10 to the 40 at 25 degrees Celsius. That's a very, very large number. That means it's a product favored reaction. This reaction almost proceeds to completion, right? Not a whole lot of hydrogen and oxygen at equilibrium. It's mostly water at equilibrium for this particular reaction at this particular temperature. So we have an equilibrium constant in terms of concentration, and we are asked to find that equilibrium constant in terms of pressure. So how can we do that, right? Well, we can do it using the formula that we just looked at, right? So I'm going to take us back to the whiteboard here, and it's going to take me just a moment to copy this. Let's see, get out of that.
Okay. The whiteboard. There we are. And okay, so I'm going to take this whole derivation mess, and it is a mess. I'm going to take this whole derivation that I worked so hard on, and I'm going to delete it, including this. I'm going to delete that, and I'm going to paste the problem, and I think I'll move my formula up a little bit. Come on. Still getting used to the software, folks. Okay. I thought I did that correctly. I don't know what's going on here. Okay, I'll just have to leave the formula down there. It's not working. All right, so we have equilibrium constant. For concentration, we want to convert it to the equilibrium constant for pressure, right? And so all we have to do here is just plug the numbers that we have into the formula to get the numbers that we want, right? And so in this case, the equilibrium constant, I'll do it in blue, in terms of pressure, is going to be this Kc term. So we're given that, right? So that's 1.25 times 10 to the 40 times RT to the delta N, right? So RT to the delta N. So let's calculate RT first, and then once we calculate that, then we can worry about raising it to the power of delta N. So RT, right? So I'll just write the whole thing out, right? So R, of course, this is the gas constant. This is something that you probably just want to have committed to memory. I've committed it to memory, not necessarily because I wanted to, but because I've done so many problems, it just kind of got branded in my brain. And that's 0.08206 liters times atmospheres over moles times kelvins. T, that's the temperature. Now, in this case, it gives us a temperature in degrees Celsius, but watch out, because the ideal gas law only works when the temperature is reported in kelvins. Notice, this is 0.8206 liters times atmospheres over moles times kelvins. This isn't degrees Celsius. So it's pretty easy conversion going from degrees Celsius to kelvins. All you have to do is add 273.15. So 200, I'll just keep it at 273 for short. So 273 plus 25, that's 298 kelvins. And we're going to raise that to the power of delta N. And again, delta N is just the sum of the coefficients for the products minus the sum of the coefficients for the reactants. So in this case, delta N, I'll just make it green over here. Delta N is equal to, well, there's only a coefficient of 1 here. 1 minus the sum of 2 and 1, right? 2 in front of that H2, 1 in front of that oxygen. 2 plus 1. So that's 1 minus 3, which is equal to negative 2. Delta N is equal to negative 2. So that means that this whole thing, this R times T, is going to be raised to the power of minus 2. So now that we have used our formula, and all we have to do is just bang out the calculations now, I'm going to go ahead and erase that, right? So if we take this 0.08206, multiply it by 298, what is that? Well, lucky for me, I've done it already. So I'll go ahead and erase this. By the way, I definitely encourage you guys to follow along and do these calculations. I think it's very, very helpful. Obviously, you know, do whatever you want. It's just my recommendation. Take it or leave it. So the product of R and T that I just erased is 24.453, and this goes on and on and on. You know, with these calculations, I think generally the rule of thumb is you don't really want to round until you get to the very end, but I think I've carried it out to enough decimal places where the calculation will still be valid. It's not necessarily important to be talking about like sig figs and stuff like that. I just want to make sure we all understand the equilibrium relationships. But anyway, so this is it, the product of R and T. So we're going to take this value and raise it to the power of minus 2. And that number ends up being That number ends up being 0.001673. And so 1.25 times 10 to the 40 minus, or not minus, times 0.001673. That is equal to, what is it? I got, now again, I could be wrong, so I prepare for these live streams pretty quickly. I don't have much time to prepare for them, especially this weekend. Like I said earlier, my 6-month-old daughter's been screaming a lot. I've been having to take care of her. It's a miracle that I've been able to do this at all. So what I'm getting at is I could be wrong, so please feel free to do the calculations yourself and check to make sure that I'm correct, or correct me if I'm wrong. I got 2.09 times 10 to the 37. So that's Kp. So again, all we did there was we understood that the equation, the relationship between the equilibrium constant in terms of pressure and the equilibrium constant in terms of concentration, and we plugged the numbers into the formula. The tricky part is that, or the part that can sort of trip you is understanding that the T needs to be in Kelvin. It can't be in degrees Celsius. And then it's just a matter of understanding the best way to use your calculator and being familiar with your calculator to make sure you don't make some calculation error. There is nothing more frustrating than understanding the concept very, very well and then getting an answer incorrect just because you weren't familiar with your calculator. Oh, that is just so frustrating. All right, so let's see. Do we have anything else? I think that's pretty much it. So that's not it. Sorry, guys. Clicked the wrong link. All right, so that does it for the live stream. Thank you guys so much for watching. I truly appreciate it. Like I say all the time, your feedback is always welcome, and feel free to mark your calendar for next Sunday. That would be Sunday the 25th. I'll be doing the next volume in my series on equilibrium. I hope you found this helpful. If you know anybody who has who needs help with equilibrium or who wants to understand this stuff, please send them my way. That would be great. And all right, that's it. So take care.